All right, so here we're going to build on what we've done before and find this sum. Now, there's one extra thing on this sum that wasn't on the examples we did in the previous lesson. The limit as n approaches infinity, okay? Before, what we had in the last example, we did n equals 10, and then 100, and then 1,000, 10,000. Here, we're going to do the limit as n approaches infinity. Now, for the sake of writing, I'm not going to write limit as n approaches infinity on every single step. We're just going to acknowledge that that's what we're going to do at the end, and I'm going to simplify this sum first.
Wait, don't you always get a constant as our answer?
We will get a constant as our final answer.
Okay.
That's where this is getting interesting. Okay? Now, if I'm doing the sum from I equals 1 to n, are there any constants in there that I can pull out first?
What's 2?
The what?
3 over n.
The 3 over n, okay? Now, I can't pull out the 2 yet because that's in this thing squared.
Okay.
Okay? But I can go ahead and pull out a 3 over n, and I'm going to have the sum from I equals 1 to n.
Wait, don't you have to square the 3 over n as well?
No, the one outside.
Oh, the one outside.
Yeah, the one outside, this 3 over n. Yeah. Now, what will I do with that parentheses inside the sum?
Split it up.
Split it up and let's FOIL it, okay? Let's split it up and FOIL it. So, I'm going to have 4 plus 6i over n is going to be, I get 2 of those, so it's going to be 12i over n, plus a 9i squared over n squared. Now, here's what I want you guys to get when you're doing this. The whole point of doing what we're doing is to be able to get it down to things that we have a formula for. Well, these are the only things that we have formulas for. I squared, and I cubed.
Or does it have I to the 4th?
If we have I to the 4th, then
Split it up.
we're kind of stuck, okay?
Okay.
Now, I think there are formulas for those. We're not learning those. Okay, but if you can do these, then if you had the formula available, you could figure out I to the 4th, I'm sure. Okay? So, that's going to be our goal here as we deal with these. Okay, so let's think this through. I have 3 things added, so I can separate that into 3 separate sums.
Okay.
Okay? So the 3 over n is still out here, but I have the sum from I equals 1 to n of 4.
That's just 4n.
Okay, that will end up just being 4n. I have the sum from I equals 1 to n of 12i over n. Now, what could I do with that?
You can take the 12 and out.
I could take that 12 over n out, okay, which we'll do. In fact, let's go ahead and just kind of do 2 steps simultaneously. We already said that that's going to be 4n. This, I'm going to pull the 12 over n out because it's a constant, and I have the sum from I equals 1 to n of just the integers. Okay? The last one, I have the sum from I equals 1 to n of 9i squared over n squared. What's the constant in that one?
9 over n squared.
9 over n squared.
So, Mr. Harrison, the formula does not apply if you have a constant, right?
Correct.
Okay.
You got to pull that constant out, and then we can use the formulas, okay? So we have all of this, and now, because I know a formula for the sum of the integers, I'm going to plug that in. I also have the formula for the sum of the squares. So we're going to plug that in. Okay, so I still have this 3 over n. The 4n is just along for the ride at this point. We've got a 12 over n times
The formula.
the formula. There you go, okay? Plus 9 over n squared times the formula for the squares.
N squared.
Times 2 plus 1 over 6.
Over 6, there we go. Okay? So, yes, we're multiplying here. So there are things that we can cancel out. Okay? Notice all the sigmas are gone now, so now we're going to start simplifying the algebra here a little bit. I don't need to get a common denominator and put it all together. Because remember, if you're taking a limit, which is what we're going to do at the very end, if I have the limit of a sum, I can split it up and do the limit of each part separately. Okay? So, let's start simplifying. This n will cancel out this n, and 9 over 6 is 3 over 2. So this whole thing simplifies to 3 times n plus 1 times 2n plus 1 all over 2n. Okay? Here, the n's cancel out, and 12 over 2 is 6. So this is just 6 times n plus 1. And this is already just a 4n. We have 3 over n. So now I'm going to distribute this in. We're going to distribute in the 3 over n. And that's going to give me a 12n over n, which is just 12. It's going to give me a plus, and I'll go ahead and distribute the 6 as well. So 18n plus 18 all over n. Okay? And then I have a plus 9 times n plus 1 times 2n plus 1 all over 2n squared. Okay? Now that's as far as I need to simplify. And now we're going to go ahead and take the limit as n approaches infinity of all of that. Okay? So, I didn't forget about this, I just didn't bother writing it on every little step all the way down. Okay? So, let's think this through. What's the limit of 12? 12. What's the limit of 18n plus 18 over n? It's 18. N is approaching infinity, so what am I thinking?
They're the same degree.
The Boba-Botten, and here they have the same degree, so it's going to approach 18 over 1, or 18. Okay? And on the last term, don't do more work than you have to. The only term I care about in the numerator
It's 18.
is the first one, the highest degree. So if I were to FOIL, I'd have a 2n squared times a 9.
18.
So that's an 18n squared plus some other stuff that I don't really care about.
Slide the top and bottom. Just 9.
There we go. So it's 18 over 2,
Yeah.
which is 9 again. So this limit equals 12 plus 18, which is 30, plus 9, 39.
Wait, add limits?
Yeah, we're adding the limits together, okay?
Can you explain the last one?
The last one, if I were to FOIL it all out and distribute the 9, I'd have 18n squared plus some other stuff.
Right.
But the only thing I care about, because the degrees are the same, is that first term. So I use the ratio of the coefficients there. Okay? Alright, so guys, that's where we're headed with all of this work with the sums. Okay? Now, where are the sums going to come from? That's what we're going to start looking at here. And you'll notice the name of this lesson was Area Above and Below. And that's where we want to start looking at what we call Riemann sums. Okay? Now, Riemann sums are a very a general term for when we are trying to find the area underneath a curve by splitting it up into rectangles. Okay? So, what we have here, we have a couple of different terms that you need to kind of make sure you understand. We have a right Riemann sum and we have a left Riemann sum. We have an upper sum and we have a lower sum. In this particular instance, we have the function y equals x squared, and we want to find the area that is surrounded by this function, the x-axis on the bottom, and then the lines x equals 2 and x equals 5. So it's this shape right here. It almost looks like a trapezoid, except it's curved here on the top edge. Okay? Now, if I were to actually find the area of this trapezoid, that would give me an approximation, but it would be too big, right? So what we've done here is we're actually going to take this and break it up, and we can actually break it up in a number of different ways. Okay? The first way is going to be by using upper sums. Okay? Now, upper sums means that we're going to be breaking up this region into rectangles, but we're going to make the end of the rectangle be such that it's actually a little bit above, it's including a little bit above the function. Now, because this particular function happens to be increasing between 2 and 5, the upper sum will always hit the right-hand side of the rectangle. Okay? The function will hit the right-hand side of this rectangle. Okay? So we have this point here. Okay? And then we also have this point up here. And there's our rectangle there.
But if you divide with infinite many rectangles?
We could, okay? And actually that's something that we're going to end up doing, because as you can see here, I divided this into 3 rectangles. Each of these rectangles has a width of 1, okay? But in order to find the height of the rectangle, I have to evaluate the function on the right-hand side. So in this case, it's f of 3.
Right.
And in this case here, it's f of 4. And in this case here, it would be f of 5. All right? So if I'm approximating that area, the area is going to be approximately 1 times whatever f of 3 is, plus 1 times f of 4, plus 1 times f of 5. Okay, well, I look at my function as y equals x squared, so that's going to be 1 times 9 plus 1 times 16 plus 1 times 25, and that all adds up to 50. Okay, 9 and 16 and 25 adds up to 50. So I have an approximation for what that area would be. Now, is that exactly what I'm looking for? No, it's too big. This area is too much. I'm including things that I don't want. Now, we already mentioned one way that we can get a little bit better of an approximation.
Use more rectangles.
We can use more rectangles, okay? If I were to, let's say, break this up. Can you guys see that? Kinda? Okay. All right, if I were to break it up into twice as many rectangles.
It's very hard to see.
Very hard to see. Let's see. Is that better?
Yeah.
Okay. So there's a rectangle, there's a rectangle, there's a rectangle. If I did twice as much, notice we're actually eliminating some of the extra bits that we got in the first example.
Aren't you adding more extra bits? It's like you have a large one that has a lot of area, but you're adding smaller ones with smaller area.
You're right, but that's what's going to make our approximation a little better, because before the first approximation included this that we didn't want, and this that we didn't want, and this that we didn't want. So we're losing some of the parts the extra bits that we had. Okay? The more rectangles we get, the better the approximation we'll get. Okay? And that's where, in that first exercise that we did, remember we took the limit as n approaches infinity? N is going to be our number of rectangles.
Okay.
So we're going to do it as the number of rectangles approaches infinity.
So if having infinite rectangles, we have the precise numbers, right?
Yeah, it'll end up giving us a precise area. Okay?
Mr.
You know what
So-
we can do?
So that is our right Riemann sum. We could do the same thing on the left. Okay, I'm not going to do all of that again, but if I made the rectangles hit the function on their left sides like this, notice because the function is increasing, this ends up giving me lower rectangles. Okay? Now the lower rectangles also give me an approximation, but what's going to be true about this approximation? It's going to be lower than the actual amount because I'm actually missing these little like triangular shaped pieces. Not exactly triangles, but okay,
So,
yeah.
can you find like the area using the over approximation and then the under approximation and just find the average?
I was just about to say that.
That's actually a great idea because we have upper rectangles, upper Riemann sums, and lower Riemann sums, or left and right. We also have middle Riemann sums, which I don't have illustrated here, but I'll show you here in just a sec. I do want to show you this part though. The area would be approximately, again I'm going to use the 1, but notice since it's left side, that would be f of 2, f of 3, and f of 4. So 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4. So that's going to be approximately 4 plus 9 plus 16, which is 25 and 4, which is 29. So notice here, we got two very different approximations, okay, using upper and lower. And actually, if I averaged them, I would get a better approximation. It still would be approximate, but it would be a lot better. And that's actually where we do have the middle Riemann sum. And that's where we can use the function. I'll just sketch it real quick here. From 2 to 5. And what we would end up doing here is instead of the rectangle hitting it on the left or the right, it would hit it right in the middle.
Yeah.
So to find the height of this, the width would still be 1, but the height in this case would be f of 2.5. Okay?
It's complicated.
And then same thing here. So it would be about there. F of 3.5. And then with this one, okay, the height of that rectangle would be f of 4.5. Now what we're going to eventually find out is, it doesn't matter which one of these we pick. If we let the number of rectangles go to infinity, they'll all approach the same value.
But, Mr. Hicks, why are you using the point in the table? Why can't you use the points? They are the vertices.
Well, because I got to use where it hits the function itself, because I'm evaluating the function there.
Oh,
Okay? All right, so that's a lot there. I understand that's a lot, but let's look at this and make sure we understand right off the bat. Do not equate upper and lower with left and right. Okay? You'll notice here I have lower sums. Some of these are hitting the function on the left, some are hitting the function on the right.
Can you hit it in the middle?
Well, not for a lower sum. Okay, but notice here, it's hitting it on the left side as the function is increasing. It's hitting it on the right as the function is decreasing. And then over here it starts increasing again and it's hitting it on the left. The whole point of this is, I'm not trying to confuse you here, but I want to make sure that you understand, do not equate lower with left or upper with right.
I
Okay.
actually wrote that.
Alright?
Evaluate the upper from right?
No,
Equate.
Don't put those together in your head. Okay? Don't put lower together with left or something like that. You have to look at the function. Is the function increasing and decreasing? And that's why a lot of times when I tell you to actually evaluate a function or evaluate an area doing this, I will tell you to use left or right, not upper or lower. Okay? Now if I do tell you to use upper or lower, you need to pay attention to where you're looking at. Okay? Now, here's what we're going to be doing. We're using n rectangles. And like we said, the more rectangles you use, the better your approximation comes out. Okay? So what we're going to actually do is we're going to actually let n approach infinity. And notice, how wide was the region we were dealing with? Well, it went from 2 to 5. So it had a width of 3. So if there are n rectangles, each of those rectangles is going to have a width of 3 over n. Okay, so if before I had 3 rectangles, so 3 divided by 3, each one had a width of 1. If I doubled it to 6 rectangles, each of them would have a width of a half. Okay?
If you're able to have infinite rectangles, would you get the exact area, or will it always be an approximation?
Because we're taking the limit, it will give us the exact area. Okay? So let's look at how this works. I think if you see it here, it'll make sense, all right?
Alright.
So notice the right and the left, okay? I'm actually, in this particular case, the right is the upper, but I'm actually going to cross that out because this formula, the way we're doing it, is for a right, whether it's upper or lower, okay? Notice what ends up happening. For the right sum,
Isn't this the same one we just did?
it is. But notice we're going to end up getting a little different approximation, but I want you to see what's happening here, okay?
Draw infinite many rectangles, right?
Yeah, I'll draw 4.
Close enough.
That's close enough.
Yeah.
All right. But you'll get what we're doing, okay? So here, this distance right here is going to be our delta x. That's going to be our change in x. All right? That is that b minus a over n, which in our case is 3 over n. Okay? Now, in this case, if I'm using 4 rectangles, it would be 3/4. Okay? Notice here, this is the challenging part, okay? This is that b minus a over n. Okay? This right here is the height of the rectangle. Okay? So I gotta make sure I have my starting point plus delta x times I. Okay? So that b minus a over n, I'm going to call that my delta x, or my width. Okay? The width.
Wait, is it width times height that we're doing?
Okay? Yeah, width times height for a rectangle. Okay? So what I have here, the x coordinate that I'm evaluating at, it's f of our starting point plus delta x times I. Okay? So that b minus a over n, that 3 over n, I'm multiplying it by the I. Okay? Now,
Oh, you're multiplying it twice. Is that it?
we're multiplying it by the I inside the function, then we're evaluating the function at that value.
Okay.
And then I'm multiplying that y value by the delta x because that's the width of the rectangle, okay? Let me just show you how this is working out. Okay? So this is going to give me the sum from I equals 1 to n of f of x is x squared, right? So this 2 plus 3i over n has to be squared.
Wait, why?
Yes. Is that
Because f of x is x squared. Okay, I'm taking f of this, so it's this squared. But then I multiply that by the 3 over n.
In general.
Okay? And guess what? That ought to look familiar, because that's what we took the limit as n approached infinity of in the warm-up problem. So what did we get for that?
39?
39, which is between the 29 and the 50 about, right?
So,
So,
Mr. Mason.
Yeah.
When we're plugging in 2 plus 3i over n into f of x, we're saying n is just a constant right now, and it's not infinity.
yeah.
And then we
You treat it as a constant within the sum.
and then we
Mhm.
only consider, we only use n as infinity once we take the limit as it approaches infinity.
Correct.
Okay.
Okay, so we take the limit, I equals 1 to n, of the 2 plus 3i over n squared times 3 over n. And that, as we found earlier, was 39.
Wait, I have a question.
Okay, yes.
Okay, if we could just, we got 39 from just like solving the limit.
Mm-hmm.
So why do all this other stuff?
Well, because you're not going to be told what to find the limit of. You're going to be given a function in a range from 2 to 5. You're going to have to, the first challenge of these problems is to write this summation. What exactly am I supposed to take the limit of? Then the second challenge is actually finding that limit. Okay?
Yeah.
So before we just did half the problem.
Wait, how did they come up with the formula again?
Well-
The 2, the plus 2.
Again, guys, hang on. How we come up with the formula, you could think of it this way. For a right sum, it's the sum from I equals 1 to n of f of a plus delta xi times the delta x.
Is it just xi times delta x?
Wait, what?
Get the right hand sum. The function of x times delta x.
No, you have to do the a plus delta x times I.
Because, I mean, normally A is 0.
And then you're plugging that into the function itself.